Hi, my name is Brecken Low Liberty, and this is my Lab 4 presentation on oscillations. So the tracker graph, as you can see here, the tracker graph shows an analysis of a mass spring system moving in 2 dimensions. The pink lines help visualize the mass's oscillation, while the program automatically plots how the mass's x and y positions change over time. The resulting sinusoidal graphs reveal that the mass is undergoing simple harmonic motion, both horizontally and vertically, showing the interplay between spring tension, gravity, and inertia. The Web VPython code, this VPython code programs and visualizes a 2D spring mass oscillation to compare a computational simulation with experimental data from a tracker video, the one previously mentioned. It creates a virtual spring and mass system where forces, motion, and energy changes are calculated using Newton's second law and Hooke's law at small time steps. The simulation updates the ball's position, velocity, and spring stretch while computing kinetic, gravitational, and elastic potential energies to verify total energy conservation. Experimental position data from a text file are plotted alongside the model's predictions to visually compare real and simulated motion on x, y, and energy time graphs. Overall, the code demonstrates how a spring mass system oscillates under gravity, showing energy transformations between motion, height, and spring stretch while confirming the model's accuracy against real data. So analysis of both the tracker and VPython code. The predicted and observed motions of the spring mass system agree closely in both x and y directions, showing similar oscillation patterns and periods with only small differences in amplitude and phase. These small discrepancies likely come from video tracking calibration limits, time step rounding, or measurement noise. The model correctly captures the 2D oscillatory motion, sinusoidal displacement, equal periods in x and y, and a consistent equilibrium shift due to gravity. The energy plots demonstrate that the energy principle is satisfied. The total energy remains nearly constant, confirming conservation of mechanical energy. The model shows clear energy exchange among kinetic, gravitational, and spring potential energy. When kinetic energy increases, potential energy decreases, and vice versa. The total energy curve stays nearly flat throughout, verifying that no energy is lost from the system apart from negligible computational or experimental errors. So what does this mean? The energy principle for your model system is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. And I said yes with a numerical and measurement error. In the energy change plots, total K and total UG plus total US are equal and opposite at each instant, and the total E stays near zero with only a tiny baseline drift expected from finite time step, calibration, and digitation noise. That behavior, oscillatory exchanges between kinetic and potential energies with total E near zero, indicates energy conservation for the model. Periods from tracker. Using the data you obtain in tracker, make 2 separate estimates of oscillation periods. First, by estimating the periods of oscillation from the x position data, and second, by estimating the periods of oscillation from the y position data. Compare the 2 estimates and discuss. Estimating from the graphs, the horizontal motion in the x direction completes about 5 cycles in roughly 8 seconds from t equals 1 second to t equals 9 seconds, giving tx 8 and tx 8 over 5 equals 1.6. Doing the same at y yields essentially the same count and span. Ty is near 1.6. The 2 estimates agree to within a few percent as expected for a single oscillator. The small difference likely comes from reading peaks by eye and slight calibration noise. Physically, the period should be the same in x and y because both motions are coupled to the same spring mass. Thank you.